Ionization energy is the amount of energy required to remove an electron from an atom. The removal of an electron definitely requires a certain amount of energy, since we have to overcome the attractive force from the nucleus to pull the electron away from the atom. However, this energy varies from atom to atom because they experience different effective nuclear charge. Let us first consider only the first ionization energy, which is the amount of energy required to remove one electron from an atom. For the trend, it involves effective nuclear charge once again. The general trend across the period is that the ionization energy increases as with greater effective nuclear charge. However, there are some deviations, mainly between group 2 and 3, as well as group 5 and 6. For ease of explanation, I will use period 2, where we will be comparing the ionization energy of beryllium and boron, and nitrogen and oxygen. The first ionization energy of boron is slightly lower than beryllium instead. The reason is tied to the energy levels of the subshells. Beryllium has a valence shell of 2s2, while boron has 2s2 to p1. The removal of electrons in beryllium is from the 2s subshell, which is of a lower energy level than the valence electron from 2p subshell of boron. Hence, less energy is required to remove boron's valence electron. The first ionization of nitrogen is slightly lower than oxygen, and this is explained using the orbitals. In this case, nitrogen, there are 2 electrons in the 2s subshell and 3 electrons in the 2p subshell, each occupying one orbital. In oxygen, the additional electron is going to be in one of the 3 2p orbitals, sharing the space with another electron. This results in a more distinct repulsion, which makes one of these 2 electrons more susceptible to be removed to attain a more stable configuration. Now, down the group. Once again, we ignore the effective nuclear charge, and instead we see the outermost electron, which is in the larger shell of a higher energy level. We can also use this intuitive understanding that as we go down the group, the average distance of the valence electron are further away from the nucleus. In both cases, we hence conclude that as we go down the group, we see a decreasing trend in ionization energy.